Hello, welcome back to the next part of our fourth lecture. We talked about the normal distribution, and before we carry on talking about the next continuous distribution, the Weibull distribution, which will be an important distribution when we talk about quality management, we first need to introduce a new concept, the hazard function, and what's that got to do with the failure rate. It's a bit tricky, so I made a simple example to explain the point. So let's think of devices that at each step in time have a 50% failure rate. 50%, I said, that's the same as a coin flip. So if you see heads, everything is okay. If you see tails, then it breaks. Okay, so we start with 4 devices, and at t equals 1, we flip all 4 coins and we see, okay, 1, 2 devices are fine and 2 break. So at t equals 1, 50% of devices break. Or that is a total number of 2 breaks. So then we carry on in time, and this is just made up example. It could be different. Let's say at t equals 2, then one other device breaks, and this one here is okay. So there's only one left, and that one is okay in the 3rd step, but then breaks in the 4th step. So all 4 devices have broken. Now, if we look at the probability density function for this whole thing, we can only show like an empirical distribution function here, because it's not a proper probability model. But if you just assume that it's like kind of the right data we get that's representative, so we got 2 breaks here in the t equals 1, 2 breaks, then 1 here, then 0, and another one here. And this is sort of the shape of the PDF, high at the beginning and then it kind of gets lower. And my CDF has this like usual shape, that's the CDF. So this kind of implies or the big question is, does the PDF going down, does that imply it gets less likely that a device breaks over time? So is it less likely a device breaks? And the answer is obviously not, because we've always kept it at 50% chance. So that's kind of this little controversy that we need to clarify. Also, if you look at t equals 1, then we've got like 50% of devices breaking. T equals 4, there's only one left, so 100% of devices break. So how does that go together with this PDF falling? And what we need for that is another concept to kind of bring those things together. We need the survival function. So an important thing is, well, if you think of the CDF, f of t, the sum of failed parts, it's all, when the probability function is or the density is the function of like how likely it is for parts to break, then the CDF is the sum of the failed parts. That means when we start here on the left, there's capital F equals 0. That's when all parts are still working. And then when we reach F equals 1, that means all parts have failed. And likewise, if we're somewhere in between, F equals, where is it? Here, F equals 0.5, that means 50% of parts have failed. Yeah, half are working, half are failed. So the CDF gives us an idea like how many working parts we still have. So what we are interested in to kind of describe the hazard function is how many remaining parts are working. So that's called the survival function, and it's simply 1 minus capital F. So capital F is the sum of failed parts, so 1 minus F is the number of working parts, or the fraction of working parts to be precise. Okay, so let's look at this second more detailed example now. So you see the PDF here, that's my thick curve, that's my PDF, probability density, and it's monotonically decreasing, just as some of them do. Some like have a peak earlier, but like this one is just monotonically decreasing over the whole time. And now the initial question was, are the chances of one specific part failing, does that decrease over time or not? And like if you look at certain time points now, let's start at here t equals 0.5, then we have to say, okay, my probability density is at 0.4, there's 0.4 here, and we have an F of 0.2, which means 80% of parts are working. Yeah, survival function 1 minus capital F, 1 minus 0.2 is 80% working. Okay, we look a little bit further in time. We look here, t equals 3.5, and there the probability density has gone down. We are only at 0.1. Yeah, this is 0.1. So only a quarter of the probability density. And what does that mean? But if you look at the CDF, that is here at 0.8, so that means survival function, we only have 20% of parts still working. Compared to before, 80%, that's a quarter. So it's not surprising that, you know, the failure rate is also a quarter. Yeah, because there are much less working parts out there. And that is sort of the idea of the hazard function. Yeah, here it's summarized on this slide. So we've got 4 times the number of parts here in the left one. So that means we also expect 4 times the rate. So the rate per working part is unchanged. So if we sum that all up, it basically we can produce a new thing that's called the hazard function. What I want to look at is how likely is it that one individual item fails. So the PDF gives me something like the absolute failure rate. Yeah, PDF. So how many fails do I see every second, sort of? Obviously it goes down because if there are very few parts left that are working, I won't see a big absolute failure rate. But I want to normalize that with a number or with a fraction of working parts. So that basically gives me then the hazard function, and that's the likelihood that an individual part fails. And that is often what you want to extract in quality management. You know, you sell parts and you want to know over time, are they getting worse, those parts? Are they kind of improving? Like we're going to talk about this in the next video. Basically the ones either they break quickly or they're kind of really, really good quality and last a long time, and all sorts of things. Just to kind of quantify or make it a bit more a calculation, what we've just looked at, a little bit hand waving. I calculated the whole thing, the hazard function, for coin flip, just like we did in the beginning, just with a lot more coins and a lot more trials. So here we've got the 2 coins, and we're looking at the probability density for first failure after T flips. So we all know if I basically have to get head, lots of heads, T times, and then I got tails, and then the whole thing, my kind of machine breaks. So the probability for this is, there's T minus 1, and at the teeth flip we break. So my probability for this to happen is P, the probability for seeing heads, to the T minus 1 times the probability for tails, which is Q, 1 minus P. This is my density, and I can draw that. I've just shown it here for P equals Q, like 50%. Yeah, that's my example. P equals Q 1/2, and it looks like that. And obviously it's another density that's like going down monotonically and going down quite steeply. Now I can produce the cumulative density function. This is a little bit mathematical trick. I don't want to show the details. It's basically, there's a formula in your formula collection for sums like that. It's a geometric sum, and we obtain this formula and we simplify it, and out comes this little piece, 1 minus P to the T. This is my cumulative density. So the hazard function, when we calculate that for our coin flip, is density, the PDF, divided by survival function. And the survival function is 1 minus F, so that's just P to the T. and f we take from above, and all that's left when we simplify the whole thing is q over p, which is constant in this example 50% is equal to 1. So constant hazard equals 1, and that's exactly what we like, how we designed the whole thing, because we always get 50% chance. Yeah, it doesn't get more dangerous or less dangerous over time. Good. In the next video we're gonna use the hazard function to talk about the Weibull distribution, how it helps in quality management.